Welcome to video presentation on detection of rootkits. We intend to give a brief introduction to rootkits and the methods to detect them. Let's start. What are rootkits? Rootkit is a collection of software tools. They are specially designed to provide the attacker with administrator privileges. They are smart enough to hide themselves and go undetected. Rootkits can be used to obtain unauthorized access to remote systems and perform malicious operations. In simple words, rootkits gain root access with help of certain software tools. A hacking process involves 5 novel steps: reconnaissance, gathering information regarding a potential target; scanning, searching the vulnerabilities of the target; gaining access, exploiting the found vulnerabilities; maintaining access for future exploitation and attacks; covering tracks to avoid detection. Once a hacker has gained access to a system, he would want to keep that access for future exploitation and attacks. Rootkits play a major role in maintaining the access. They are silently present in the system and are undetected. Essentially, rootkits provide an attacker with full access via a backdoor. They hide the intrusion. They can modify any software in the system, even the one meant to detect them. They conceal other malware, notably password stealing, keyloggers, and computer viruses. Also, they can appropriate the compromised machine as a zombie computer and use it for attacks on other computers. Rootkits can be classified broadly into user mode rootkits and kernel mode rootkits. Earlier rootkits worked in the user mode, but most of them have been abandoned now. Today, most rootkits found on the compromised systems are kernel based, operating in the ring 0 level. First, they transfer the malicious code into the kernel. Once in the kernel, they manipulate the system calls and hide the attacker. Now, let us understand the way rootkits intrude the system and the methods we must adapt to detect them. User mode rootkits. User mode rootkits use two main techniques. One is the manipulation of log files and the other exchanging system binaries. Manipulation of log files. The log files contain information regarding the activities of the rootkit tool. Now, since the rootkit wants to hide its presence, it should delete this information to ensure its presence. For this, the attacker provides a few keywords and the rootkit program scans various log files and deletes all lines in the log file containing the keyword. This keyword may be any information related to the attacker. Let's see how this can be done.
Here we show you how rootkits modify system log information. Here we run a small piece of code written by us, which is similar to the one found in rootkit tonkit. It's named as tonbs. It changes the messages file found in the log directory. Let us see how this is done. Before doing so, let me show you the contents of message file. Yeah, these are the last 6 lines of the message file, and in the last line it says accepted password for seg. This seems to be due to activity of tonkit, and it's used this seg name to log in as user. Now what tonbs does is tries to find all the lines which contain seg as keyword, seg is the word, and delete those lines from the log files. We run the piece of code. It takes as argument the keyword. You need to be a root it seems to have done the job. Let us check it. Yeah, the last line, which is here, the exit quit password for seg, is being removed. In this way, the rootkit tries to hide its presence from the administrators.
Exchanging system binaries. In order to hide the files and processes of the attacker, rootkits substitute the system binaries for manipulated versions. For example, consider ls command. This is used for file listing. The rootkit puts a manipulated version of this command so that no file related to the attacker is listed. Similarly, ps command and nested commands are replaced by modified versions. As a result, the ps will forget some processes while nested drops some network connections from the output. Now, let us investigate the ways of detecting these mishaps. User mode rootkit detection. As we understood previously, the user mode rootkits manipulate log files and system binaries. The configuration files and system binaries of a system have unique hash values called MD5 or checksum. Though the manipulated binaries may have the same length and timestamp, they will definitely differ in their checksum values. This fact is used to uncover possible intrusions. Now, let us see a demo.
I want to show you a famous rootkit detector called CHK rootkit. It's a very great tool. It checks for rootkit by comparing MD5 sums, searching for default configuration files of some famous rootkits like the one here, say Romanian rootkit or wall, gold 2, etc. It also checks for TCP and UDP ports and also checks for hidden processes. Now we shall show you a small Python script written by us that performs some of the rootkit detection tasks. This also checks for MD5 sums. It compares with the standard values and sees if it is modified. And it also looks for some default files of some famous rootkits. It also checks for hidden processes in some directories. So hidden processes may not always indicate the presence of rootkits, but it's better to have a look at them.
Kernel mode rootkits. Having looked into user mode rootkits and their detection techniques, now let us get started with kernel mode rootkits. Kernel mode rootkits directly jump into the kernel and manipulate the innermost core of the operating system. They tweak the system calls in their favor and intelligently hide themselves from being detected. Kernel mode rootkits are much tougher and stronger than user mode ones. Detecting them becomes impossible sometimes. They are nightmares for administrators. Intrusion. There are two main methods by which kernel mode rootkits intrude into the kernel. They are code injection and flow of execution. In code injection, the rootkit is loaded into the kernel as a module and the regular interface provided by the operating system is used. In flow of execution, the rootkit modifies the pointers of the system call. As a result, whenever the system call is made, it will be redirected to the rootkit. Code injection. Before explaining this technique, let me introduce you to some of the technical terms that would be used. They are interrupt descriptor table IDT, system call table, kmalloc. IDT is a data structure used to implement interrupt vector table. It is basically a table of interrupt handlers. Syscall table is an array of pointers to system call functions like sysopen, sysread, syswrite, etc. kmalloc is a function internal to the kernel. It is needed to reserve space in the kernel memory. The whole idea here is to use kmalloc function to get some space in kernel where the rootkit can be installed. Intrude in the kernel. Through IDT, attacker gets the reference to syscall table which has pointers to system call functions. Then one of the system call functions, say sysunion for example, is modified to incorporate the kmalloc function. Now this sysunion is called, which internally calls kmalloc function and hence allocates memory in the kernel space. Now the rootkit occupies this part of the kernel memory and starts its malicious activities. Flow of execution is another method of intrusion. Consider the execution of the program ls. It uses the system call open to access directory for reading. The flow of execution is as follows. The ls makes a call to open function. This generates an interrupt which makes the system switch into kernel mode to handle the interrupt. The interrupt descriptor table IDT is referenced and the corresponding interrupt handler is called. The interrupt handler references the syscall table to finally call the function sysopen. This is the usual flow of execution. But if the rootkit is present, it manipulates the syscall table to divert the execution of the system calls to its own code. This is the most widely used method by the attackers to change the flow of execution in the kernel. Countermeasures. After understanding the catastrophic damages a rootkit can make, it is quite natural to start thinking of the possible countermeasures. We all know that prevention is better than cure. Let us look into some preventive measures. Deactivation of loadable modules. Many rootkits will simply fail to operate if the dynamic loading of drivers via the module interface is deactivated. But since no drivers can be loaded into the kernel at runtime anymore, administrative overhead is created at the same time. This is more feasible on server systems where new drivers are rarely loaded. Some rootkits can still be loaded via dev/kmem. Protecting dev/kmem. Since there are many ways to access the device file dev/kmem, the only effective protection can be provided by mandatory access controls. To do this, there are special kernel patches available. Now, we shall see some detection techniques. Checksum and special rootkit detectors. This method is similar to the one explained for user mode rootkits. Critical kernel structures. In this method, the critical structure of the kernel is saved and compared with offline copies to detect the presence of rootkits if any. kstat is one such tool which checks for the integrity of syscall table. Code injection method generally modifies the addresses of the system call functions. kstat tool can detect these changes. Runtime measurement of system calls. Many rootkits employ complex algorithms to hide the presence of the attacker. As a result, the infected system call would take more time to execute than the original system call. This can be used to detect the presence of rootkits.